of the University of Nottingham to pursue her PhD in development of fiber optic pressure sensors in healthcare applications. And as a postdoctoral research fellow in the Biomedical Engineering Department of Nottingham Trent University, she has further developed fetus movement monitoring belt using fiber optic sensing technologies. And in 2021, she joined Lumentum Limited UK, which is a market-leading manufacturer of innovative optical and photonic products, enabling optical networking and commercial laser customers worldwide. She's currently working as a fiber optic research engineer, contributing to the development of fiber optic transceivers and chips. Over to you, Dr. Chalani.
Wow, that was a lot, right? Thank you, Dr. Chaudhary, for the great introduction, and Professor Shant and the committee for selecting me as a resource person for this webinar. And I'm really honored to have been invited by the Institute of Physics Sri Lanka for their monthly webinar. And thank you all for taking your best effort to turn up today during this bizarre moment in Sri Lanka. So without further delays, let's crack on. Can I have my next slide, please, Dr. Chaudhary?
Presentation mode, please.
Still, I cannot see it. Okay. So this is the out. So you can see, you all can see the outline, right? Outline slide. Is it?
Yeah, now it's.
Is it visible now?
Yes.
Okay, so this is the outline of my talk today. Because I'm going to talk about fiber optic pressure sensors in healthcare applications, so I would like to give you all a brief introduction of how fiber optic sensing works. And also, when it comes to healthcare application, there are various types of different fiber optic pressure sensors available in commercially and also under academic research. So I would like to walk you throughout these different types of sensors. And then this is followed by a discussion on advantages of fiber optic pressure sensors over the other competitive technologies, which is then followed by a discussion on fiber optic sensors in healthcare application and where it really stands. And the rest of the topics will be focusing on my research work. Can I have the next slide, please? Okay, so how fiber optic sensing technology works? If you take any sensor, it's a device basically that can measure any biological or chemical or any physical parameter safely and reliably, right? For example, a sensor can tell if the fetus in a womb is healthy or not, or maybe it can measure blood pressure or glucose level, or it can even tell you sometimes check the healing rate of a wound. So you can think of anything basically. However, fiber optic sensors provides many advantages over the other commercial available biosensing technologies which are in the market. So I'm going to talk about that in my next slide. Fiber optic sensors were first introduced around 1960, mainly for endoscopic and cardiac application. But more importantly, in the last years, the expansion has been greatly benefiting from the development of telecommunication and fiber optic communication, in particular, which are offering high quality, miniaturized and affordable optoelectronic components at very competitive prices. So this figure in this slide shows the mandatory building blocks of a fiber optic sensing system. It has a light source. It could be a coherent light source, such as a laser or any incoherent light source like an LED or tungsten white light source, depending on the application. And then you have the input optical fiber and the output optical fiber. It can be just one single fiber depending on the application. Like we can use it in a reflection mode if we like. And then the important bit is the sensing element. And we also have the photoelectric detector, typically a photodiode, and then the signal processing unit. However, so the essence of this is that the light is sent from the light source to the sense element through an optical fiber. And then the properties of light, such as intensity, phase, or wavelength or frequency, will be modulated at the sense element by the measurement. And this modulated signal is sent to the photoelectric detector or the photodiode. And the necessary signal processing is done at the signal processor to demodulate the signal, and that's how the measurement is done. Can I have the next slide, please? What are the advantages of fiber optic sensors in healthcare application? So recent developments in the biomedical field have been driven by healthcare trends such as minimally invasive surgeries, miniaturization of the medical devices, automation of medical therapies, and using robotics in surgeries, or wearable sensors, smart textile, so on and so forth. Fiber optic sensors are an ideal candidate for fulfilling most of these requirements. So one of the great advantage of fiber optic sensors in healthcare application, it's biocompatibility. So fiber optic sensors are made from silica, which is an inert compound and a very stable compound, therefore unreactive with most of the substances, and therefore it makes a biocompatible and non-toxic non-toxic when it comes to a healthcare application. And this is an ideal candidate for biomedical sensors to be used in applications like minimally invasive surgeries or therapies. And also they can be sterilized with standard sterilization procedures. Another attractive character about fiber optic sensor is that they are lightweight and flexible in nature, along with their small diameter, which allows them to be used for most of the invasive and in biomedical applications, for example, in catheters or endoscopic tools. So if you take a bare fiber, typically the diameter of a single mode optical fiber is about 125 microns. However, with the necessary fiber protection coatings and fiber jackets and the polyacrylate coatings and the stuff, it can goes up to a 250 micron diameter. And they are also easier to adhere to bones and biological tissues, and therefore OFS sensors have been developed to measure the deformation of bone due to strain in certain research studies. And another great advantage of fiber optic sensors are they are immune to electromagnetic interference because they are made with electrically insulating materials. So One of the great advantage is that they can be simultaneously used with technologies like magnetic resonance imaging MRI, or optical coherence tomography CRT or OCT, sorry, in that kind of applications. And also it provides remote monitoring capabilities. So you can have your sensor in one place and the monitoring device in another place if you like. And it also allows multiple parameters. For example, you can measure temperature, humidity, or pressure using one single fiber, because it allows multiplexing capabilities, and having multiple FPGs or multiple cavities, it allows multiple parameter sensing. Can I have my next slide, please? So where is the fiber optic sensing stands in the industry and research? So as I was mentioning before, healthcare technologies are globally expanding and growing day by day, demanding for advanced diagnostic features. For example, for in vivo measurements of specific biophysical parameters, sensors are packaged in medical catheters and operated as standalone devices. Particular applications are cardiovascular, urologic, gastrointestinal, and neurological application areas. And they are also very effective when paired with other medical devices, usually for real-time monitoring of surgical procedures, via alternative techniques like MEMS, microelectromagnetic systems, or imaging fails. Particular examples are endoscopy, robotic surgeries, and thermal ablation. Lastly, fiber optic sensors can operate external to patients in form of a smart textile or a wearable device, or embedding in a wound dressing, for example. So such sensors has that ability to continuously monitor biophysical parameters without requiring an invasive positioning of the sensor, and they could be integrated with smartphones as well. So this picture on my right-hand side describes the level of maturity of fiber optic system for different applications. So the commercial systems existing for intracranial pressure, IAB, and femoral artery applications, and these represent basically the most successful cases of biomedical fiber optic sensing. And the other pressure sensing applications in like urology, gastroscopy, vascular stenosis measurements are in their major research stage. And the measurements of temperature and pressure in like thermal ablation procedures, and force sensing tools for robotic eye surgeries, and wearable smart textiles have been recently consolidated as a key research trend with near future commercial prospects. And on the other side, research in personalized drug delivery and assisted by biophysical sensors, and in long-term monitoring of prostatic implants are at their early research stage. Can I have my next slide, please? So fiber optic pressure sensors can be broadly categorized into three main types. The first one is the intensity-based pressure sensors. So these were probably one of the first pressure sensors to be commercialized. So the working principle is fairly simple, and it's based on the variation of light intensity at the amplitude. So as you can see in this picture, an optical fiber with its tip placed in front of a movable reflecting membrane, and the optical fiber guides the light of the source to the tip of the fiber, and then the influence of the measure and the original membrane distance to the fiber tip changes, and hence the intensity of the reflected light that coupled back to the same fiber, or if you like, you can have another fiber parallel to this, can be modulated. So the intensity of a fiber the light coming out from the reflected light can be dependent on various parameters like the core diameter and the position of the fiber, as well as the numerical aperture. But it also directly depends on the distance between the fiber tip and the membrane. So the light intensity increases rapidly from zero when the diaphragm is in contact with the fiber end plane, and then it reaches to a maximum when the diaphragm plane matches the position where the solid angles of these two numerical apertures intersects most, as you can see in this picture. And as the diaphragm plane moves further away from this, less light is collected back, and intensity decreases slowly back to zero. So by properly designing the sensor for a selected pressure range, providing that the only monotone region of the light intensity curve is used, a unique pressure could be derived from a light intensity once the sensor has been calibrated properly. However, these are not so popular nowadays because due to the fact that light intensity always dependent on a lot of uncontrollable factors. For example, the measured intensity is directly linked to the light source, which could fluctuate due to the aging or temperature changes. And the same applies for the detector side. Can I have my next slide, please? Sorry. So the next type of fiber optic pressure sensors are fiber Bragg grating sensors, and they are basically made bilaterally exposing the core of a single mode fiber to a periodic pattern of intense laser light. So this exposure procedure makes a permanent increase in the refractive index of the fiber core, creating a fixed index modulation according to the exposure pattern. And this fixed index modulation pattern is called a grating. So as you can see here, when the light launched into the fiber, at each periodic refraction change, a small amount of light is reflected. And at the end of the fiber, this reflected light signal combines coherently or superimpose coherently to one large reflection at a particular wavelength, and when the grating period is approximately half the input light's wavelength, and this is referred to as the Bragg condition, which you can see in the right-hand side bottom, that equation. And so, however, the light signal at wavelengths other than the Bragg wavelength, which are not phase matched, are essentially transparent. They will cancel off. Can I have my next slide? So you can see what you can see here is a bare fiber without any FPG in it. So once this input spectrum is launched into the fiber, what you can see at the other end is the same because there is no change to it. But if you see the next one, next slide, please. So here you can see, so there are two FBGs in this in optical fiber. So the input spectrum, what is reflected is two peaks, which are centered at the Bragg wavelengths. And if you see the transmission spectrum, you can see two troughs there, which satisfies this Bragg condition. So one important thing about FBGs is that they are not directly sensitive to intrinsic pressure, but instead they are sensitive to axial strain. So whenever an FBG undergoes a strain, it will basically change the grating period and hence change the Bragg wavelength. However, FBGs can be used as pressure sensors if the pressure can be transduced to axial strain. And I will discuss this in my next slides, how this is done in our research work. Can I have my next slide, please? Yeah. So the third type of pressure sensors are fiber optic fabric pero pressure sensors. So from a commercial point of view, this is one of the best OFS technologies for pressure sensing, especially for in situ in vivo pressure measurements, because this allows the device miniaturization and it offers highest design flexibilities, etc. So as you can see, a fiber optical cavity is made at the end of the fiber, and a reflective pressure sensitive diaphragm is attached to the tip of the cavity. And as the input light travels through this fiber cavity, it will experience multiple reflections, and you will see an interference fringe pattern coming out from the fiber at the end. So any change into this cavity length causes the interference fringe pattern to shift. And if the cavity length is changed by the measurement, the reflection light could be able to modulate accordingly. Can I have my next slide, please? Thank you. So this is some maths I've been using to simulate a fiber optic pressure sensor during my studies. Don't worry, I don't want to go through this now because I don't want to put you into a sleeping mode. But what I wanted to emphasize here is a wavelength maxima of the reflection interference fringe pattern is a function of the cavity length. As you can see, the bottom relationship, lambda max is directly proportional to the cavity length. Next slide, please. So this is the simulation I have done. As you can see, when the pressure is applied, cavity length changes because it's the pressure sensitive diaphragm. And therefore you can see the blue curve shows when there is no pressure is applied, but the other curve shows how interference fringe pattern shifts as the pressure is applied. Next one is the same, I believe. Yeah. Okay. While I was pursuing my PhD at University of Nottingham in the fiber optic sensing research group, I have been studying mainly on 2 different fiber optic pressure sensing technologies depending on the type of application. Fiber optic fabric pressure sensor technology, especially more suitable for fluid pressure sensing. Where fluid pressure is the pressure exerted by a fluid per unit area perpendicular to the surface. And this is very important in certain measurements like blood pressure monitoring, intra-abdominal pressure measurement, or bladder pressure measurements. And secondly, I have also studied fiber Bragg rating sensors, which are specially suitable for contact pressure measurement. And this is the pressure exerted by one object on the other when they are in contact. And this is important application like compression therapy, prosthetics, or pressure ulcers. Next one, please. So let me now focus on my fiber optic fabric pressure sensing related work. So the proposed sensor configuration is shown in the left-hand side top. The fabric cavity is at the tip of the single mode fiber and applying a pressure sensitive Perlin C diaphragm. So in the cavity creation, 2 techniques were investigated. Focus on beam to mill a cavity at the tip of the fiber. And the second one is to splice a fiber capillary to the single mode fiber and cleaving it under a microscope to create the cavity. And right-hand side picture shows how the film attachment is made. Can I have my next slide, please? So focus on beam milling technique were used to form the cavity as one technique because FIB provides the most precise and maskless and micro nano fabrication tool. So in focus on beam technique, a highly focused gallium ion beam column is basically used to mill or to image a sample inside a vacuum chamber. Typically, its spot size is around 10 nanometers, which provides high precision in micro and nano fabrication. So most of these FIB systems are integrated with electron beam, as in a scanning electron microscope, which allows imaging during the processing. Can I have the next one, please? So in this method, a fiber capillary this one, the second method is splicing of fiber into a capillary to create the cavity at the tip of the fiber. So in this technique, a fiber capillary was spliced into a single mode using a fiber splicer, as you can see here. So what a splicer does is fusing 2 fibers together, and once it's fused with the capillary, it was cleaved under a special setup, as you can see here under microscope. And you can see in your right hand side bottom the sensor created, of the cavity created using this method. Next slide, please. So once the cavity is created, using this kind of setup, the film was attached to the tip of the fiber. Next one, please. And this shows here So can I see the next slide, please? So this one shows here the experimental setup that has been used to calibrate the sensor. So we have a commercially available manometer, which was used to calibrate the sensor, and fiber was enclosed in a pressure chamber and infused with air using an infuser. And simultaneously interference fringe pattern was obtained and logged along with the pressure changes. So the figure in the top left, blue line, top right, sorry, blue line corresponds to the reflection spectrum without application any film to the tip of the cavity. And the orange one shows how the interference fringe pattern looks like after the application of the diaphragm. And bottom right picture shows how the interference fringe pattern shifts with the pressure. Next slide, please. And this shows the two sensors have been made with their sensitivities. Can I have the next one, please? So during my PhD, I also developed a mathematical model for a highly sensitive FPG contact pressure sensor. So what is the importance of a contact pressure sensor, and why do we need to develop a mathematical model for this? So for example, the UK on average spends about 40 to 380 GBP per patient for treating pressure ulcer, and the mean healing cost per patient can range from 1,200 to 14,000 GBP. So I can bring you various examples like this when it comes to contact pressure sensor in healthcare. But what I wanted to emphasize is this is a huge cost, and therefore these condition deterioration could be greatly reduced by a continuous monitoring of contact pressure. So our research group was trying to address this issue by coming up with a novel FPG sensor, which you can see in the next slide. Next one, please. So the proposed sensor you can see in your right-hand side bottom picture. Usually, as I was saying before, bare FPGs are less sensitive to contact pressure. So in our work, we present enhancing the contact pressure sensitivity by embedding the FPG in a polymer patch. And this will transduce the contact pressure into axial strain and hence increase the sensitivity of it. So in this sense, sensitivity depends mainly on how efficiently the pressure is converted to axial strain. And this mainly depends on the mechanical and physical parameters of the polymer layer. Therefore, during my PhD, I've developed a mathematical model integrating transmatrix method and finite element analysis to optimize this sensor. Next slide, please. So as you can see here, this shows the results I've obtained. So this mathematical model was validated over the experimental results, so it agrees with the experimental results really well. So the final conclusion I have been made with this work is embedding a 3mm FPG centrally in a circular disc patch with a diameter of about 5.5 millimeter and a young modulus of about 20 megapascal. The sensitivity can be increased by a factor of 7 with respect to the initial design by our group, and also it can be increased by a factor of 270 with respect to a bare fiber. Next one, please. So while I was working as a research fellow at Nottingham Trent University, I was working on a project of developing a fetus movement monitoring belt using fiber optic sensing technology. So the motivation for this work was we all know that the stillbirth rate of a country usually determines the quality of the maternal and healthcare of a country. So according to the WHO records in 2015, annually 2.6 million babies are still born across the world. So one of the major problems faced by obstetricians is identification of women who are at risk. So a maternal perception of fetal movement is a widely deployed marker for the fetus well-being, but sometimes the counting performed by moms are prone to errors for various reasons, such as less concentration or the position of the fetus in the womb. And there are very limited number of devices available for mothers to track this at home. For example, National Health Services in the UK uses a counting app. So they ask the mom to press a button if she feels a baby movement. But still, when the mother is busy or sleeping or less concentration or for various other reasons, this might not be able to track this efficiently. And therefore, we proposed a counting wearable belt using FPG sensors, and we developed a very preliminary prototype for this. Can I have my next slide, please? So as you can see here, this is the belt on a volunteering mom. FBGs are embedded in the belt, and so FBGs are sensitive to strain. Any change in the strain due to the baby movement can be related to a change in the Bragg wavelength. And this could even track the breathing pattern, as you can see in the top right figure. When there is a kick or any kind of rolling movement is detected, the initial breathing pattern is distorted, and by carefully designing the necessary DSP, we would be able to figure out what type of movement that was, and even we can get rid of the artifacts. So next slide, please. So this brings to the end of my presentation, and I would like to thank and acknowledge University of Nottingham and Nottingham Trent University for enabling me with all the necessary resources which I needed for my academic research. Thank you everyone for your attention throughout the webinar. Thank you.
Yeah. Thank you very much, Dr. Chalani. It's a very interesting presentation and it's an impressive work. If anyone would like to ask any questions, please do ask now.
Hi, Chalani. This is Hasula.
Hi.
Did you do any work on LPG sensors by any chance?
No, I haven't worked with LPGs. LPGs are mostly used in chemical sensing, so I haven't touched that part. No, sorry.
Okay. Also curious to know if you have any collaborations with Slintech, which might be doing FPG sensors and LPG sensors.
With Slintech, sorry, I didn't get that.
Yeah, so I understand that Slintech might be doing fiber optic sensors, FPG sensors,
Oh,
or
really?
LPG sensors. Yes, so I was wondering if you
okay.
have any collaborations with them.
Yeah, maybe in future that seems interesting. So let's see.
Yeah.
Let's have a chat after this.
Okay, good. Good.
Yeah, thank you.
Any other questions?
Charlie, I'll ask a couple more questions if everyone else doesn't mind.
That's
Could you
fine.
tell us a bit, could you tell us a little bit more about the light source? Did you use a swept wavelength interferometer interrogator, or?
No, I have been using a spectrometer basically from Ocean Optics, and
Right,
I've been so yeah, basically yeah, we haven't designed any integration technique for this one specially, yeah, but we are looking forward to do it.
Okay. Does Lumentum have interest in doing interrogators as well? Maybe that's a cheeky question.
Yeah, to be honest, I don't want to talk about anything about Lumentum, because if I want to talk about that in public, I may need to go through all these lawyers and the stuff. So I don't want to talk about, yeah, sorry about that. But we can
That's
have
okay.
a chat later, yeah. Yeah, that's fine.
Good. All right.
Hello, Chalani. Can I ask
Hello.
one question?
Yeah.
From my knowledge, I think fiber brand ratings are subject to bending errors. So if you bend the fiber, that will create some sort of a
Yes, but yeah, obviously, I mean, a bending can obstruct the light path, but there are bending in sensitive fibers, and since these are protected with many layers, so sometimes it's not very much sensitive for those kind of application, and we can remove the artifacts as well. So
okay.
there have
So
been bending sensitive fibers, yeah.
right.
So
in your
bending
work,
is a problem for anything when it comes to fiber optics, basically. But yeah.
so in your work, it wouldn't matter that much, is it?
No, it didn't matter because we were using a bend in sensitive fiber optic sensors, basically.
So how about the sensitivity of contact pressure scanning
Pressure sensing, you mean, sir?
Yeah, yeah.
So the sensitivity, so for a, actually I can't remember the figures right now, but if you take a bare FPG, so we can, it's basically very less sensitive. We can say it's insensitive to the intrinsic pressure, but embedding in my work, so embedding in a polymer patch, it was increased by a factor of 270. So it was increasing the sensitivity greatly by embedding FPG in a polymer patch, because it has that ability to transduce that in transverse pressure into an axial strain. So it was increasing the sensitivity greatly. I can't remember the sensitivity of a bare FPG. I have to look back the figures, but yeah, it was increasing greatly.
Okay. Any more questions?
On the fabrication side, do you think that making cavities for Fabri-Perot type of sensors, is it cost effective to make cavities using fib, or is there a better way to get it done?
So that may be not the best cost-effective method to do that, but you can, when we are doing the milling, we can reduce the cost by having multiple sensors on a particular stage and doing the milling in one go, because we have to have that vacuum and the stuff. So it is to make it time effective and cost effective, we can we can have a couple of fibers in one particular stage and do the milling at one go. So we can do in that way. But the most cost effective way of creating the cavity is the second method, I would say.
Okay, thank you.
Any more questions? If there are no more questions, let me thank Dr. Chalani for her presentation. Also, I would like to invite our Joint Secretary, Dr. Vasanthi De Silva, for the vote of thanks.
Thank you very much.
Thank you, sir. So good afternoon, everyone. So I would like to thank our guest speaker of the IPSL August seminar, Dr. Chalani Abeywardene, accepting our invitation to share your research experience with us. So your talk gave a deep understanding of how operate these fiber optic pressure sensors and their interesting application. More impressive part is how these concepts and the mathematical models play a major role in the industrial applications. So it's very honor to us, one of our Sri Lankan scientists contributing her research experience with the commercialization stage. So it will highly impact on the development of the world. So once again, we're grateful to have your talk for this evening, Dr. Chalani.
Very much. Thank you.
So I would like to thank IPSL committee members, those who are organizing this webinar series continuously. So dear participants, thank you very much for your time and the attention throughout this webinar series. Have a nice day. Thank you all.
Thank you.
Thank you very much.
Thank you.